It's Paul Bamberg welcoming you to the first of many R scripts for Math23c. This one's numbered 1M, M for math, because it illustrates some of the mathematical ideas that I will be going over in lecture. You can watch this video before the lecture, after the lecture, or maybe you'll choose to watch the two R script videos in between the first and second lectures each week. Whatever works for you is fine. This is designed to be accessible to students who've never done anything in R. If you learned R in Math23a, there's going to be a fair amount of redundancy here. Notice the pound sign starting these rows. Any row that starts with a pound sign is a comment. It's not executed as R code. I've commented these scripts fairly heavily. It may be that if you're experienced with R, you can extract full value from the script by just running it yourself, not listening to me, just reading the comments. So I'm going to show you how to build some truth tables in R using an R construction called a data frame, which will be key to data analysis when we get into that. And the first truth table I'm going to build is one for the logical operation not. The first thing I did was to define a vector p, and I did that by concatenating the two truth values, true and false. I assigned that to p. Equals will work for assignment, but it's a little bit risky. So I try always to use this left arrow construction. With a semicolon, I can have two operations on the same line. So I save this vector in a variable called p, and then I display p, and if you look down here, p contains the two values true and false. The logical operation not is represented in R by an exclamation mark, and I can try it out on true and false. To do that, what I do is to position the cursor on this line, hold down Control, and hit Enter. And if you look below, you'll see that not true turned out to be false, not false turned out to be true. However, in R, most operators and most functions will act on vectors, a component at a time. So let's try applying not, the exclamation mark, to the entire vector p. Let's store the result in a variable named not p and display it. There we go. And it worked. It turned true false into false true. And now we can make something that looks very much like the truth tables in the lecture notes. I will make a data frame whose first column is the vector p, whose second column is the vector not p. I will assign it to the variable not table and then display it. Presto! We have the truth table for the operation not. It takes truth values p in the first column and converts them to their logical negation. Now we can do the same thing with and with or. Now we're going to need 4 rows, however, because we need the 4 possible combinations of true and false. I'll do this in a rather heavy-handed way by just concatenating true, true, false, false to make p. And then for q, I want true, false, but I'm lazy. I'm going to type it in as tf, tf. And you see it displays as true, false, true, false. Why does this work? It works because R predefines t as a variable whose value is true and predefines f as a variable whose value is false. If you ever assign new values to capital T or capital F, this will no longer work, and for that reason I tend to stay away from it. I once spent about an hour helping my summer school students track down a bug in an R script from another course which eventually turned out to be a consequence of the fact that the instructor in that course had used t for true, and in my course earlier in the day, the students had set the value of t to something else. Now, when you look at and or in R, you discover there are two possible operators. And can either be a single ampersand or a double ampersand. And the one we want is the single ampersand. It's a so-called vectorized operator. It operates on vectors component by component. And to see that, we will take P ampersand Q, assign it to P and Q, and display the result. And we get true, false, false, false. That's correct. We got the true value only when both P and Q had a true value in the first position. If I do the same thing with the double ampersand, I get just true. This is not a vectorized operator. I can feed it two vectors, but it pays attention only to the first component. There's a similar situation with OR. The vectorized operator is a single vertical bar that produces P or Q. It produces true, except in the case where both P and Q are false. If I use a double vertical bar, it looks only at the first component. That's not what we want. And now we can assemble this all into a nice data frame, which I've called and or table. And nice, huh? It looks just like the ones in the lecture notes. I have columns for P, Q, and then the values of P and Q and P or Q. I can now do an automatic check on a famous identity of logic, De Morgan's law, which says if you take P and Q and apply not to it, the result is the same as if you take not P or not Q. How do I check that? All I have to do is make two vectors, the first of which is not applied to P and Q, the second of which is the result of applying OR to not P and not Q. How do I know where to put the parentheses, you ask? Well, my rule is I always put in parentheses even if I suspect they're unnecessary, and then I'm sure in what order the operations are being carried out. So I get the same results in both cases. That proves De Morgan's law. Well, let's go to three variables. Now it's really getting tedious to type in something like true, false, true, false, true, false, true, false. So let me introduce you to a couple of other operations in R that produce vectors. Rep is short for repeat. Rep2, 4 means repeat the value true 4 times. So this says repeat true 4 times, repeat false 4 times, concatenate the results, and store it in P. 4 trues followed by 4 falses. This next one says make the vector true, true, false, false, and repeat it twice. And the last one says take the vector true, false, and repeat it 4 times. But it turns out there's a very nice way of doing this automatically using the R operation expand grid, which basically takes Cartesian products of its 4 or fewer or more arguments. So this says take the vector with true and false 4 times, combine the components in every possible way, and make a vector that has all the results concatenated with one another. We'll call it grid 4. And when you look at grid 4, you'll discover that you get 4 columns. The last one has 8 trues followed by 8 falses. The first one has true, false, alternating. And the 16 rows of this contain all possible ways of selecting true or false from each of the 4 vectors. This isn't quite what is conventional for truth tables because usually in truth tables you have the last column varying most rapidly and the first column being the most stable, but I can fix that easily enough. I don't like these names var1 through var4 anyway, so let me take the fourth one, store it in P, the next one store it in Q, the next one var2, store it in R, var1 will store in S, put it together, see what we've got. And this is actually quite useful if we want to experiment with truth values for functions of 4 logical variables. This is the right initial setup. So let's save it. To save it, I use the R function write.csv, which says take the data frame truth4 and write it as the comma-separated variable file truth4.csv. This just has the trues and falses separated by commas. On your own time, you can look at this either in a text editor or in Excel. Microsoft Excel will happily load and save these CSV files, and they're going to be our standard way for getting data into our R scripts. The first time I tried this, it failed. It said I didn't have access to the place I was trying to write it. If that happens to you, first check that you followed the instructions for setting up your options, that you've specified the data file in your Math23c directory. If you've done that, then what you probably need to do is close RStudio and restart it. That worked for me. Just to check that this has worked, I will use read.csv to load this into a new variable, which I've called reload, and display it. Now let's move on to the slightly trickier topic of disjunctive normal form and conjunctive normal form. I'll make my 3-variable truth table again with P, Q, and R, and add to this a 4th column where I have put T and F rather capriciously in the 8 positions. I'll put everything together into a data frame, and now we have an interesting question. What is the standard Boolean algebra expression for the function represented by the 4th column? That is, what function of P, Q, and R will give the result Z? There are 2 standard ways of answering this question. That is, there are 2 standard ways of converting a truth table into a Boolean expression. The simpler of the 2 is so-called disjunctive normal form. And to create disjunctive normal form, what you do is you focus your attention on the true values in the column for Z. The first one, the 4th one, and the 7th one. And you ask, how can Z be true? Well, one way that Z can be true is P is true, Q is true, and R is true. But there are other alternatives. The next alternative is we could have the conditions for the 4th row that P is true, but Q and R are both false. That is, not Q and not R are both true. And the final alternative is row 7. Not P is true, not Q is true, and R is true. And if I OR these together, I get something that is a Boolean algebra expression for Z. Let's try it out. Well, it came out right. True was in positions 1, 4, and 7. Conjunctive normal form is a little bit trickier for most people. Let's look at that data frame again, and this time focus our attention on the 5 rows for which the value of Z is false. What we want to say is that none of the conditions for any of those 5 rows occur. How can that be? Well, look at row 2. If not P is true, we can't have a true in that position. If not Q is true, we can't have a true in that position. And if R is true, then we can't have a false in that position. And any of those 3 things will kill off the row. So we can say, we can guarantee that the conditions for the second column are not satisfied if not P or not Q or R. Now look at the third column. The third column cannot occur if any of 3 things happens. If not P is true, that is P is false, or Q is true, that kills off the true false there, or not R is true. And in order to be sure that we never get the result false, what we have to do is AND these 5 cases together. You can check the others on your own. And that gives us a rather complicated Boolean expression for Z, which is, when we evaluate it, exactly the same as what we had before. True in positions 1, 4, and 7. Let's finish up by doing a little bit of logic with finite fields. Remember, in order to switch over from Boolean algebra to finite fields, we say true is represented by 1, false is represented by 0, and that's exactly what R likes to do anyway. If you use a logical value in an expression that calls for arithmetic, true is automatically converted to 1, false to 0. We will exploit this mercilessly throughout the term. So I'm going to build P and Q for setting up a truth table as before. And now let's look at P times Q. This is a bit bizarre. I'm taking logical vectors and multiplying them. And what's going to happen? Well, it's going to multiply component by component, 1, 1, 0, 0 by 1, 0, 1, 0. Should get a 1 only in the first position. And it does. And notice the answer is 1 rather than true, because what it did was convert the logical values to arithmetic and then do multiplication. Ordinary multiplication works fine in Z2 because anything times 0 is 0 and 1 times 1 is 1. In the finite field Z2, however, ordinary addition isn't quite what we need. Ordinary addition says 1 plus 1 equals 2. The rule in the finite field Z2 is get the result by ordinary arithmetic, divide by 2, and keep the remainder. So 1 plus 1 is equal to 0. R lets you define your own binary operators. It's a rather strange syntax. You have to put the name of the binary operator in quotation marks, and it has to begin and end with a percent sign. So I'm saying I want to use percent plus percent to be the function of 2 variables, x and y, that adds x and y together and then takes the result modulo 2. If you did R in Math23a, you're already familiar with doing this for finite fields, and you may recall that percent times percent has already been used by R to denote matrix multiplication. Well, let's check that we've been successful. We ask it to try all the addition facts, and when we look at the results, we see that yes, indeed, we got 1 for 0 plus 1 and 1 plus 0, 0 in the 2 other cases. Now we can build the truth table for OR, reload P and Q, and using finite fields, the function that represents P or Q is P plus Q plus P times Q. I have to use our special plus sign so that 1 plus 1 equals 0. And I also learned the hard way that I have to put parentheses around P times Q, otherwise the operations get done in the wrong order. And what do you know? We got 1, 1, 1, 0, which is exactly the result applying the OR operator to this pair of vectors. Let's finish up by showing that the correct formula for P implies Q is 1 plus P plus PQ. I will take 1 special addition P, special addition P times Q, and save it in implies. And then I will make a data frame out of P, Q, and implies. And you can see that is the correct truth table for the implies operator. P implies Q is false only in the case where P is true, but Q is false. Well, that's one of the most bizarre introductions to R ever, but I hope it reinforces what we're doing with logic in the lectures and has been a nice introduction to data frames, logic, and vectorized operations in R.